Hello and welcome to day 3 of the second week of the CAS Virtual Showcase. You have joined the Keynote webinar entitled, How Does Artificial Intelligence Really Work? This webinar is part of the CAS Virtual Showcase, which is a 2-week window of webinars designed to support the CAS community. I'm Wendy McLeod and I am the CAS Community Outreach Manager for communities across London and the East of England. Joining me this morning is the presenter of our session, Simon Peyton Jones. Simon is a leading computer science researcher at Microsoft Research in Cambridge, where his main research interest is the design and implementation of functional programming languages. He has been deeply involved in computing education at school since Computing at School was launched in 2007, and he still serves as CAS's chair. He chaired the working group that wrote the programs of study for computing in 2012 and was appointed chair of the National Centre for Computing Education in 2018. During the session, please use the question window on the right-hand side of your screen to ask questions. All attendees are in listen-only mode. The top of the window has an orange rectangle which can be expanded or collapsed. If using social media, the hashtag for the event is hashtag CASVirtual20. I'm now going to hand over to Simon for the session.
Great, good morning. Thank you, Wendy. It's a joy to be with you all virtually. Thanks for coming. I think computer science is just the most exciting subject on the face of the planet, and I hope to convey a little sense of that excitement in this talk. But let me start by showing slides here. So I want to take the lid off the box of all this hype about AI to let you understand a bit about what's inside it. And to do that, I just want to tell you why I want to do that. So here's the program of study for computing that you're all busily teaching, that says rather ambitiously that all children from primary onwards should understand and apply the fundamental principles of computer science. And it's fair to ask, well, why? Why bother to do that for all children? And I think it's this, that some elementary understanding about the natural world and the artificial world that surrounds us underpins our ability to operate well in that world. So in the case of natural science, it enables us to make good judgments about our decisions as citizens or as politicians or as individuals. And in the computing sphere, it underpins our ability to use digital systems effectively and safely, and particularly to exercise well-informed judgments about them. Like, is this the right technology? What risk might it entail, and so forth. And this is particularly so for artificial intelligence, which is all the rage at the moment and does have a whole bunch of stuff about what it's appropriate for and what it's not. And if nobody understands anything about how it works, you can't make well-informed judgments. So I think it's important that everybody has some understanding. This is too important to leave to geeks like me. So let's just focus then on AI, and I'm going to whistle along. Please do ask questions as we go. I will pause and give Wendy a chance to break in and ask me any, but I'll be sort of monitoring as well. I may even ask you questions, so please stay alert and engaged. But we will finish on time nevertheless. So, artificial intelligence, machine learning. Here's the sort of popular view about machine learning. You show this magic box, a cat, and it outputs something that says, yes, it's a cat. If you show it a dog, it says, no, it's not a cat. So there's some sort of mysterious magic process inside that recognizing cats from pictures. Somehow, we do it intuitively, somehow computers are doing it too. So the trouble with the magic box story about digital technology is that it disempowers us. As Arthur C. Clarke said, any sufficiently advanced technology is indistinguishable from magic, and magic is something that is like we intone or incant a spell and hope it works, but we have no idea of its consequences or its limitations or how to adapt the spell or change it or what it might be good for or not good for. So this sort of just treating things as magic, not good. So my goal here is to take away the magic, right? To give you an understanding of what happens inside the magic box. So in an hour's time, you will know what is inside the magic box. So machine learning then, it's just a way to get a computer to do something you want done. which is what programming is for, right? But machine learning and programming are really quite different ways to get a computer to do what you want to do. It has different strengths and weaknesses than programming does. So let's contrast the two. Here's programming. Suppose you wanted to write a program to recognize cats, right? You wanted to write it in Python or Java or something. Well, you think about what data structures would you use? What algorithms would you use? Would you maybe try to make a recognizer that would look for the pixels and find pointy bits for ears? And maybe you would look for eyes and see if they were in the right place. And you sort of somehow do feature analysis and try to figure out what bits of a cat were which. Well, this algorithmic approach, the step at a time, all the intelligence in me, I just write out a step at a time program, works quite well for some things, video games, databases, so forth, but it works really very badly for recognizing cats. It is not a good way of writing cat recognizers. So the machine learning approach is really very different. The magic box contains two things: a pretty simple program. Oh, by the way, a cat recognizing program written in Python would be, thousands of lines, hundreds of thousands of lines, really a lot if it was going to recognize cats really well. But in machine learning, the program is very small, right? A few hundred lines, maybe a few thousand at most, but pretty small program, right? But it's controlled by a lot of floating point numbers. They're part of the data that the program uses as an input, and really a lot. That's 100 million floating point numbers. It's sort of typical for these machine learning programs. And then the idea is that you give this simple program thousands and thousands of pictures of cats, and you somehow adjust the floating point numbers so as to make the program reliably say this is a cat and this is not a cat. And I'm going to show you in this talk how that program works, what the floating point numbers do, and how we might adjust them to make it recognize cats well. Okay, yes, you will be able to get a copy of the presentation, both in video and on slides. Thanks, Steph. So this is very different to traditional programming. Instead of writing step by step, the program is fixed. The thing that we change is the numbers, right? Don't worry about the fact I'm calling them floating point numbers. Just think of them as numbers, but not integers 1, 2, 3, 4, but real numbers like 1.7 or 1.893. So how can this possibly work? A simple program with lots of numbers, how could that possibly recognize cats? And once we figured out how it could, what could possibly go wrong? And that's the purpose of this talk. So here we go. I'm going to show you a machine learning program to recognize good biscuit recipes. And these are going to be particularly simple recipes. I'm going to make biscuits with only flour and butter and sugar. And the recipe is X kilograms of flour, Y kilograms of butter, 1 minus X minus Y kilograms of sugar. So I make in 1 kilogram of biscuits altogether and bake, right? That's my recipe. And so the magic box I want is going to take in X and Y and spit out good biscuit or bad biscuit, right? Is this a good recipe or a bad one? Okay, that's the goal. So you might imagine plotting these on a little sort of scatter plot here, with the horizontal axis being the amount of flour, the vertical axis being the amount of butter, and then I put a dot for each experiment. I make some biscuits and I feed them to my children and I see what the expression on their faces is. And I'm going to use orange dots for bad biscuits and blue dots for good biscuits. And then I might make a little table, and this is going to be the training data that says, and each row of the table is one experiment. 1.2 bits of flour, 4.3 bits of sugar, bits of butter, verdict, bad, right? And so forth. So I make lots of that. That's the training data. There's no substitute for training data in machine learning. You need a lot of it. So I'm going to experiment on my children, make lots of biscuits, and then hopefully get a scatter plot like this. Now, if I had a scatter plot like this, how might I then make a recognizer that given a new amount, a new XY pair would tell me whether it was good or bad? Well, one way to do would be to draw a line that separates them, right? Here is my training data, if I draw this red line, now if I have a new point, a new XY point, I could say, is it on the top side of the line or the bottom side of the line? Top side means good, bottom side means bad. Easy, right? So how might I describe this line? Well, let's see. We're used to drawing graphs and lines, and here's what you would usually do in Key Stage 3 maths. This is the line y equals ax plus b. So a is the gradient and b is the intercept on the y-axis. This is sort of good, but it's actually not very good in this context because it's not very good when we get to lines that are fairly vertical. If it's fairly vertical like this, you need a very large gradient. So a gets to be really big, And computers don't work very well when they work with really big numbers. Or at least it's sort of, from this point of view, it doesn't really matter which way the line, everything's symmetrical. There's nothing special about it being vertical here. So having massive numbers for that seems uncomfortable. So here is a very standard idea, an alternative way to describe a line. So this is the first point at which something that may be new to some of you. Here's a way to describe a line using three numbers, A, B, and C. And it's the line described by ax plus by plus c equals 0. X is the x-axis, y is the y-axis, the vertical axis, and c is some constant. So on this line, ax plus by plus c is equal to 0. And you could rearrange this equation to make y the subject of it, right? Easily enough. Oh, screen sharing, question mark. Helen, I'm not sure what your question is, but I'm sharing slides. I hope you're seeing slides all the time. Is that, Wendy, is everybody seeing slides?
Yes.
Yes, that's fine. Okay,
yeah,
cool. Thank you, Dan.
Yeah.
No, Helene is not. Sorry, Helene. I think I'll carry on and leave you and Wendy to work that out somehow.
Yeah, no problem.
Okay, so this is just an alternative way to describe a line, but it's a way that works much better when you want vertical and horizontal lines. So tell me what happens if B is 0. Would anybody like to? So you can respond by typing a question here. If B is 0, what does the line look like? Any ideas? What line is described? So that would just be ax plus c equals 0. Vertical. Chris, you are right on it. Yes. So if B is 0, we get vertical lines, and we can move it from side to side. And if A is 0, we get horizontal lines. So this is nice because it means we can get vertical and horizontal and everything in between by mixing A's and B's. So this is what we're going to do. Moreover, it's kind of nice that we can, that if we got a new XY pair, if we calculate AX plus BY plus C for this new XY pair, if it's bigger than 0, it will be above the line. If it's less than 0, it'll be below the line. So bigger than 0, good biscuit. Less than 0, bad biscuit. So once I've decided on A and B, those, by the way, are the numbers for this machine learning program. Once I've learnt A and B, then if I have a new biscuit recipe, new X and Y, I compute X plus BY plus C equals 0, and that tells me whether it's good or bad. Positive, good, negative, bad. And in fact, it tells you how good or bad, because a little bit of work with geometry and maths tells you that the distance from a point PQ to the line is this little expression I've written on a slide, AP plus BQ plus C over the square root of A squared plus B squared. That's the distance from the line. So that's very nice too. That so we can say if it's very positive, that means it's far from the line. So maybe you're confident about your prediction. So I kind of like this, but it's a way in which, here's a bit of computer science, but it's using, key stage 3 mathematics. This particular thing, distance from a line, we probably don't cover as part of the curriculum, but it's not hard to work out. I've given you a Wikipedia reference here. Okay, so far so good. I don't see any other questions at the moment. Please ask questions if you're lost. I really don't want you to get lost. We will somehow finish even if I answer questions. So here is summary where we've got to. The magic box is simply going to compute AX plus BY plus C, where X is the amount of flour, Y is the amount of sugar, and it's going to spit out a number that may be positive and may be negative. If it's positive, I'm going to say good biscuit. If it's negative, I'm going to say bad biscuit. And A, B, and C are just some fixed numbers. Once I've learned A, B, and C, then I'm going to feed it lots of recipes. I'll spit out good and bad. But during the learning process, I'm going to try to figure out what A and B and C should be to make it make good predictions. So I hope that's okay. Please yell now if that is not clear. No visible yelling, as it were. Okay. So the trick is, how can we learn? It's called machine learning. What does learning mean? Well, as I've said, it means that we adjust A, B, and C until we get as good answers as possible. Now, what does as good as possible means? It means we're going to minimize something. So we're going to minimize something that in machine learning circles is called the loss. Now, what is the loss? It is the number, here we can think of it as the number of mispredicted biscuits in our training data. So we got training data, and we're going to try to arrange that we mispredict as few as possible. Right? We might mispredict some because the training data might be noisy or complicated, or maybe even wrong, right? There might be some bits in our training data that's just outright wrong. So, but we're going to try to adjust A, B, and C to minimize mispredictions. Okay, so how are we going to do that? Well, I'm going to show you, before telling you how, I'm just going to show you an example of actually doing it. This is a little, this is a website called TensorFlow Playground that you can play with afterwards. The URL is on the slide, and it really has. It's showing on the screen, I hope now, a picture on the right of the of my biscuits and a little neural network. Now, the little box in the middle where it says 1 neuron is the magic box, right? When I click on play, this at the top right-hand corner, you can see that so something happens and the bottom left-hand corner goes orange and top right. So it's learnt. Now, how is it learnt? Well, if I hover my mouse over these little wires that go into that magic box, you'll see weight minus 0.4. That's A. Here you'll see weight is minus 0.72. That's B. And here there's a little gray dot. It says bias is minus 0.25. That is C. So here's A, B, and C. And it somehow learnt those in a mysterious way. And I can just refresh and start again and refresh. But each time it is learning afresh. This bit up at the top right-hand corner, test loss is a measure of the number of mispredictions. And you can see that it goes to 0. Training loss is the number of mispredictions on the training data. It has a separate set of test data, and test loss is the how good it worked out in practice. Okay, so I think that's enough for TensorFlow Playground. Let me go back to, but you can maybe play with this. If you get bored during this talk, you can go and play with TensorFlow Playground. So training loss is the number of mispredicted items in my training data, and then usually I keep separate a test data, some sort of stuff that I haven't given during training, and that's what I'm going to use to measure, have I really learned well? Okay, so how are we going to learn? Well, we're going to do it like this. We're going to start off with some values of A, B, and C, maybe randomly chosen initially. Then I'm going to pick one mispredicted biscuit, and then I'm going to somehow tug A, B, and C to make the line mispredict a bit less much. And the trick is, how do we do the tugging? So we're then just going to pick a misprediction, tug a little bit, pick a misprediction, tug a little bit, pick a misprediction, tug a little bit, and just keep doing that. That's the algorithm. It's pretty simple. This is machine learning. Now, remember so the question is, how are we going to do this tugging? How should I adjust A, B, and C? So here's the whole thing again. This is the entire program. X and Y are input. I compute AX plus BY plus C to produce R, and I want to adjust A, B, and C to make it more correct. Now, so a key idea is maybe I should adjust by most the parameters, that is the A, B, and C's, that most strongly affect R. Let me say that again. Adjust by most the parameters A, B, and C that most strongly affect R, the output. Because the output is what I'm trying to change. I'm trying to tug the output in a good direction. So I might want to change by most the parameters that affect R the most. So when I say most strongly affect, what does that mean? Well, it means something about gradient, right? It's like the steepest gradient is most strongly affect. So here I've finally resorted to using actual mathematical notation. It's the sensitivity of R to changes in, let's pick A as being the one we're interested in. How sensitive is R to changes in A? If I make a little change in R, so if I make a little change in A, how much does R change by? If I make a little change in A, how much does R change by? And that's what this funny dr over dA means. It means how much I change R if I make a little change in A. Well, since this is a pretty simple function, AX plus BY plus C, if I make a little change in A, How much does it affect R? The gradient with respect to A is just X in this case. That's what tells you how much it's affecting A. And the gradient with respect to B is just Y, and the gradient with respect to C is just 1. So this is not covered in GCSE mathematics, but it will be. But essentially, it's just taking the gradient with respect to one, with respect to A, or with respect to B, or with respect to C. So intuitively, it's quite a simple idea. How sensitive is R to changes in A? How sensitive is R to changes to B? And I can quantify how sensitive by a number that says if X is big, then R is very sensitive to A. If X is small, R is not very sensitive to A. And that's really all the intuition you need from this slide. Okay. Chris asks, do we get rid of the mispredictions? Well, if we tug enough, we may be able to get rid of all the mispredictions in the training data, unless our model doesn't have enough capacity. And I'm going to get to that. We'll see. So I guess the answer is no, we may not be able to get rid of all the mispredictions, Chris. We'll see. So here's our algorithm now. The learning. Now this is the learning algorithm. I'm going to do a number of steps. Pick a mispredicted biscuit, find the R, and then I'm going to adjust A, B, and C, like on this slide. I'm going to say A gets to be A plus a little alpha times X. So alpha is going to be something small, like 0.01, right? And X, why did I choose X? I chose X because that was on the previous slide. It said that's how sensitive the R is to A. Right, so when I want to adjust A, I want to adjust it in proportion to its sensitivity to X, and similarly for B, and similarly for C. And alpha here is a sort of small number that's the learning rate. It says how fast do we tug. If alpha was big, I would move A, B, and C by a lot. If alpha was small, I would move A, B, and C just by a little bit, And so moving it by a little bit is fine, because I can then pick another thing to learn, another mispredicted biscuit, and tug again and pick another mispredicted. So it slows down learning, but it means you don't overshoot so much. So typically you might start with a big alpha and make it smaller. So it's a sort of bit hocus pocus. Choosing your alpha is, who knows? You just have to suck it and see. Nevertheless, alpha is the learning rate, and we typically start it large and make it small as we keep iterating this process. So pick a biscuit, adjust A, B, and C according to this. Pick a biscuit, adjust A, B, and C, pick a biscuit, and again, keep doing that. That's all. So here's the whole algorithm. This is the machine learning algorithm. And the particular adjustments in step 3 here are governed by the particular box. This box only contained R equals AX plus BY plus C. If you have a more complicated box that does more calculations, the adjustments will be more complicated, but the idea is precisely the same. And this step 3, the calculate the adjustments and do this little tugging, that's called back propagation. So now you can impress your friends when you go to parties. But it's pretty simple. I want to stress, this is the core of machine learning. It's incredibly straightforward. So let's see. If I just iterate this is when I did TensorFlow Playground thing. That is exactly what was happening. I won't show it again, but that's all that happened. Now, to Chris's question, what can go wrong? Can we get rid of mispredictions? Well, let's see. If my training data has no data in some areas, I'm going to learn nothing about what happens to those recipes, right? So here, I've just chosen all my training data to be in, the top right-hand corner and the bottom left-hand corner. So I know nothing about the top left and the bottom right. It might be that they're good. It might be that they're bad. Who knows? We're going to learn a line, but the line is really not going to be very truthful about these areas because it just doesn't know. Nevertheless, it will make a prediction. So therein lies the trouble, right? If you train face recognition software on white faces, it might not recognize faces very well when you give it black faces. And that's a classic example of biased training data. But it's so clear in this simple setting. If you don't give it the data, it can't possibly learn from it. This is a real problem in practice. Another thing that might go wrong is you might simply have chosen the wrong things to put in your training data. So maybe the most important thing about the quality of the biscuits is how long you bake it for, or what temperature you bake it at. Maybe the amount of flour and sugar and butter, hey guys, any amount will work, go mad. What matters is you bake it for an hour. In that case, my predictions, but if I only measure flour and sugar, I'm going to get good biscuits and bad biscuits all mixed up. So to Chris's question, then I'm going to mispredict a lot because there's no line that's going to separate them. Right, at least that one, we can sort of tell that things are going wrong because we get a lot of mispredictions in our training data. And that's just two things that can go wrong. There are a lot of others. You could have the first one I've shown you is not enough training data or unrepresentative training data. Oh, not enough might mean, oh look, I only gave you 2 experiments. Well, I'm not going to learn very much from that. I need to do lots of baking to learn anything, and then it needs to be representative. We've discussed that. Then it might need enough model capacity, and I'm going to show you an example of that shortly. But before I do, I'm just going to say that these are only some of the challenges, right? There's a whole lot of other stuff, flat spots and local minima. There's local minima, just quickly say, whenever you're doing a minimization process, what am I doing? I'm tugging things. I'm trying to make something smaller, right? I'm trying to tug, make something smaller. So if I was doing that on a, imagine a sort of line that goes down and then up and down a long way, I might get stuck in a sort of false valley. If you always walk downhill, you may not end up at the bottom of the mountain. You may just end up, at in a lock halfway up the mountain, what's those, on a hanging valley, right? So only if you're prepared to go up a bit can you then go down again. So you can get stuck in false minima or local minima. So there's an incredible amount of literature about how to do this loss minimization process effectively, and there's lots of ways in which you can go wrong. And annoyingly, it can be quite hard to know when you even have gone wrong, right? Because you get a magic box that makes some predictions. How do you know if they are, if one of these gone wrong things has happened? Sometimes it's easy to tell, but sometimes it's really hard to know, and it can even be harder to fix it. So I'm just pointing out, incredibly simple setup, but the ramifications here are numerous and complicated, and it can be hard to tell when you've done a good job. Okay, let's go back to TensorFlow Playground. What happens if the biscuits look like this? All right, so now the good biscuits are in the middle of the picture, and the not so good biscuits are on the outside. Now it's pretty clear that a line is not going to be good at separating the good biscuits from the bad biscuits. But it's also pretty clear that if you showed this to a human being and said, guys, here's a PQ point in this scatter plot. Is it in the good cluster or the bad cluster? You would have no problem with saying if it's near the middle, good. If it's near the outside, bad. Right? Can we do that with machine learning? Well, it seems simple enough. Maybe we could use 2 or 3 or 4 lines and somehow combine their votes. How would we combine their votes? Well, let's try this. 2 or 3 lines, let's just take 2. So each line is represented by one of these magic boxes, ax plus by plus c. So we'll have 2 of them, and then we're going to combine them. Now, how can we combine? Well, what's in the question mark? Well, guesses, any guesses? Anybody like to suggest what might be in the question mark? Hint, look on the slide. You can type suggestions into your question box. Take an average, yes, that could be reasonable. Add them together and divide, yes. Anyone else? Take a maximum or something? Who knows? Okay. No, nobody else is willing to put their head above the parapet. Well done, Chris. Go to the top of the class. Or we could average, or we could add them up. Oh, use the same equation as in layer. Yes, very good. We could reuse something. We could maybe just reuse the same idea. Maybe we could just have a second magic box in effect, because after all, the first magic box was combining an X and Y and producing us something. Now we've got a P and a Q. maybe we could just use another magic box. Hey, like this. Oh, let's see. Let's see. Maybe like this. Maybe we could just do some combination. Yeah, it's just a third magic box that combines the P and the Q, and that would incidentally be so taking an average would be included in here. That would be A is a half, A3 is a half, and B3 is a half, and C3 is 0. That would then be P over 2 plus Q over 2. So we just add them up and divide by 2. So that subsumes averaging, but it does more besides. Ratio of P plus Q to P plus Q. Yes, very good. There's all sorts of things we could do. But it's not quite clear how to choose. But let's see, since we have the idea of magic boxes and this linear combination has worked pretty well to make a line, the idea of using a second magic box is quite attractive. But this part, circles. Yes, so good point, Tom. We could instead try to use a circle. And that could be another possibility, but instead we're going to approximate circles with lines. I don't know anybody who's tried circles. Good question. Now I'm out of my depth, but I'm going to show you how to just essentially use the same idea all over again. Now, let's see. The example I'm showing here definitely will not work. Right, simply doing another magic box as shown on this slide cannot possibly work. Can anybody see why this will not work at all? It's sort of one of those insights that once you've seen it, it's just completely obvious, and until you see it, you just can't make heads or tails. This is a non-starter. No X and Y. No X and Y. Oh, well, let's see. The X and Y going in at the front, and then they come out as P and Q, and they go into the third box. But but the reason that this isn't, if you imagine wrapping, I should have drawn a slide about this. Imagine wrapping the whole thing, wrap a box around all three. Now it's a box that has X and Y as inputs and R as its output, but a linear combination of linear combinations is just another linear combination. If you do the algebra, you will find that if you write out the algebra for the output, you'll find it's just something times X plus something else times Y plus a constant. So in other words, these three magic boxes behave no differently than a one magic box with a different A, B, and C. So we can't possibly learn anything better than one magic box can. So this was a big insight in the early days. It's sort of, if you like, it's a replication of itself. Yes, it doesn't make any progress. But then an amazing insight that was quite early in machine learning, about 20 years ago, was this. All we need to do is to stick on the output of the first layer of magic boxes this thing called ReLU, which stands for rectified linear unit. And ReLU is an incredibly simple function. If its input is smaller than 0, its output is 0. If its input is bigger than 0, it leaves its input unchanged and just spits it out. So I've given the definition in the top right-hand corner of this slide. So ReLU is an incredibly simple thing. It just cuts off anything below 0 and makes it 0. The key thing is it's not linear. And so when you combine it into, with a third magic box on the output, a third linear combination, you don't get a linear combination. And rather remarkably, this simple idea turns out to be enough to learn virtually anything. It's astonishing. This is all you need to do. Again, there's lots of variations. It could be, people often use TANH or something else, but this is enough. And I'll show you it in action on TensorFlow Playground. Here it is. So here we go back to TensorFlow Playground. So now I'm going to do the circular data. Here it is. With my one neuron, what happens? Well, it tries to learn. Oh, it does learn a line of some kind, but look at that loss at the top. The training loss is still 0.37. Lots of mispredictions, even in the training data, and even worse in the testing data, the test data. Oh dear, one line hasn't worked very well. Well, TensorFlow Playground lets me add more layers. Look at that. Wow, 2 layers. And now maybe I'll make 2. Oh, damn, I didn't mean to do that. I meant to add I wanted to add one more neuron in the first layer and take away one here. So now I've got 2 in the first, so now I've got the picture that was on the slide. Let's see if that works any better. Ooh. Now you can see it's actually running live. You can see the epoch on the right. This is the number of iterations it's done. It's sort of learned to line. Somehow the losses are still not very good. No, I mean this is quite hard data to fit even with 2 lines. So let's try adding some more neurons. Let's have 3. Does that help? Maybe 4. Let's have a go. Run it. Ooh, this is exciting. Wow, isn't that spooky? It has learnt a with 4 linear combinations here and just 1 to combine them. It has managed to learn a really good fit for this data. Look at the loss, suddenly down to 0.0. Isn't that amazing? I think it's kind of like that's when you think, oh wow, computer science is kind of magic. Let's see, would it work if I had 3 neurons? Let's try, just run it. So what I like about this program, TensorFlow program, is you can play around with things. Ooh, it sort of learned something a bit weird. Ooh, but as it's going on, things are still changing. Maybe, I think in my experiments, it's sometimes managed to do better than this. Let's try exactly the same thing, but I'll try it again from scratch. When I say from scratch, the difference is that I start with different A, B, and C. Wow, this time, bingo. So do you see that? See what happened there? It started with different values of A, B, and C. All the A, B's, and C's, it started randomly initialized. One run, it learned from the training data, picked mispredicted biscuits, and it didn't learn anything very well. Second time, it learned it brilliantly, right? So this is a sort of randomized algorithm. It doesn't always do the same thing every time. Let's try it again. It's kind of fun. So you can do this in your spare time. In fact, you can show it to your children and just enjoy and try playing around with more neurons or fewer neurons. Now, this you can see, this again hasn't done very well. It's sort of learned a bit. So it looks as if maybe having more neurons in the first layer seems to make it get there more quickly, right? So it seems more reliable. So, and the truth is that in the machine learning world, there is a lot of suck it and see going on. You know, there's a lot, they spend a lot of time doing exactly what we're doing, namely building neural networks and repeatedly running them against vast quantities of training data to see how fast they learn. And you can play here with by adding more neurons and seeing what it does. Oh, this is a bit funny. It's all very exciting here. And when I said that, do you remember I said there was that ReLU thing on the output of the inner units? At the top here, there's a little box that says activation, and at the moment it says TAN-H. I should maybe have changed it to ReLU. ReLU is one of them. That was the one I told you in the talk, and so I'll run it with ReLU. But it's not the only one that people use. Oh, interestingly, it makes sort of you can see the lines more clearly here, can't you? Because you get sort of corners to the box that it learns now. I'll just running it again. You get something different. Running it again. Oh, this is exciting. Get something complete. Wow. Now it's gone completely bonkers this time, hasn't it? Hasn't learned anything. Training loss, very high training loss, very high test loss. It's completely lost. Better start again and try it. Oh, doing a bit better. Anyway, you get the idea. Let's see. Oh, this really happens in real systems. This is an incredibly tiny machine learning system, but you can see lots of interesting phenomena that you can explore experimentally. And real machine learning people spend a lot of time doing exactly this kind of experimentation on large quantities of data. So going back to the activation thing, this is using ReLU. TAN-H, which is hyperbolic tangent. What have hyperbolic tangents got to do with machine learning? It's just a non-linear function that you can plug in those yellow boxes that I had on the slide. And apparently, in this particular application, it does seem to work a little better. I haven't the faintest idea why. But mostly, the particular nonlinear function that you use doesn't matter too much. Here, they've got 4 standard ones. And mostly, I think most machine learning systems use only those 4 at most. I'm not going to talk about regularization at all. Okay, any questions so far? We are now getting a shape and not a line. Are we looking for area shapes? Oh, we are getting a shape and not a line. So we are, in fact, it's really important that we do learn. We're trying to learn the area where the good biscuits are. in response to Chris's question, right? And the area where the good biscuits are is indeed a little shape inside. And it might be a funny shape like, oh, what about this? Now, could I learn, now the good biscuits are in the corners. Let's try that. How well can I learn this? Ooh, spooky. With 4 neurons, I seem to learn one lot of good biscuits, but I've totally failed to find the other lot. So yes, Chris, I'm learning a shape, but I may need to learn multiple shapes. This one looks a bit harder, right? Now I'm still trying to find the good biscuits. Oh, you know, I'm really not going to do very well on this. But maybe if I add some more layers and I add some more neurons to those layers, let's just suck it and see. Away we go. And you can see that something exciting is happening. You should do this at home because it takes quite a while to converge when you get a really complicated picture like this. But I think you can see that some rather amazing, spookily wonderful things are happening here. It can become addictive. Okay, let me go back to the talk. Fractal, is it? Is it a fractal? I've no idea. No, I think it's not a fractal in the sense of self-similarity at every level. Okay, I'm going to go back to slides because I should finish up. I don't want to completely run out of time. So yes, okay. The key point about all of this is that I really want you to focus on is that the learning process works exactly the same as before. Although there's more complicated things inside the box. Here's the box, right? The box now is the whole thing. All of this is the box, right? And I'm going to do that differentiation process with respect to the entire box. So the more layers I have, the more complicated the function I'm differentiating, but the learning process is the same. Differentiate it, adjust the weights based on those derivatives. Now, in practice, how does this work? Well, the reason that machine learning has become in vogue and relevant and applicable and useful in the last 5 years is because of scale. We've known a lot of this for 20 years, but we just didn't have the computational scale to run it on a big enough scale to do useful things. So much so, in fact, that people thought maybe neural networks just weren't up to it, but they could never try it at scale. And so now we can try it at scale, and it really, scale matters, right? This is a in a typical image recognition benchmark, there might be 150,000 images of all sorts of things, each of which is tagged with quite fine-grained information. Like in this particular image database, I'm thinking of the 150,000 images tagged with things like Persian cat, tabby cat, African elephant, Indian elephant. So it's quite fine-grained. It's not just cat or elephant, and it's not just yes, no either. It's which of these 1,000 different things, chairs, cats, bottles, animals, cars, which of these 1,000 is it? A typical neural network that will recognize this has 150 million weights. That is those floating point numbers, the A, B, and C. Well, we had 3, A, B, and C. We got up to maybe 9 in the end. These things have 150 million of them. They have 20 to 150 layers of neurons. They have to classify one image, that is to run the neural network forward to, let me see, to, in my picture here, to take an X and Y, calculate the output of the first layer, feed that to the next layer, calculate that output. Just doing that might take 20 billion floating point operations to classify an image. Remember, an image itself consists of a lot of pixels. So there's a lot of computation just to classify one image, let alone how long it takes to learn, right, to adjust those weights. But each adjustment weight takes lots of classification. But remarkably, neural networks can, with these 150 layers, get the right answer out of 1,000 possibilities right first time in 70% of the cases, and they'll get the right answer will appear in their top 5 predictions in 90% of the cases. It's quite remarkable, quite remarkable. Now, Steph asks, is this really learning? That's a sort of philosophical question, right? There's no sense in which the machine is doing anything like that we might think of as learning, or my student might think of as learning. It's just adjusting floating point numbers, right? There's nothing, it's not really understanding anything. On the other hand, if you look at these layers of networks, you can sometimes retrospectively say, oh, it looks as if that layer or that neuron has somehow learned to recognize eyes. People do this with neural networks. They somehow sort of look at them and try to say, what has it figured out? But it's not because it's worked out, it's saying, I know it's an eye. It's because that's just the best way to get the floating point numbers to fit. The real numbers to fit, was the numbers of permutations and computations that predict the most likely result based on a statistical calculation. What does it actually mean learning? No, I think the best I can do, Steph, is to say that it's just this iterative process of adjusting 100 million numbers or 150 million numbers until they do the best job of predicting. And we might call that learning, because it's hard to, when it's finished, it really remarkably it does seem to have learned to recognize cats and elephants, but it's not learning as we would think of it when we talk about students and teaching. And yes, Julie, this whole neural network, Julie asked, layers of networks in the computer equated with neural networks in the human brain, action potentials and movement of electricity around the brain. That is indeed the inspiration from which the original neural networks 30 years ago, Jeff Hinton and his colleagues, and Chris Bishop and so, did indeed design them, right? They did come from the brain in the first place, right? So whether this rendition of neurons into computational form and then this mechanism of learning, is that what the brain does? We sort of think it might be, but I think it's, I think that's probably still an open question. Steph asked, maybe AI, artificial intelligence, is still a long way off. Let me see. So in fact, perhaps that's what I should leave this final slide up while we're talking to some of these questions. We have still a few minutes for questions and discussion. So is AI a long way off? Well, again, it depends what, so that Steph asks. So it depends what you mean by AI. If you mean, can you train a computer to reliably recognize, weeds when it's in a weeding machine so that it digs up the weeds and not the corn? The answer is actually probably yes, we can do that right now. Is that artificial intelligence? Well, you might say we've trained a computer to do it, so therefore it can't be artificial intelligence. But certainly, I think 30 years ago we thought, wow, that's pretty cool. I wish we could do that. If you mean capable of intuitive jumps and generalization, I mean, there is a sort of generalization going on. In that once we've trained it to recognize cats, you can show it a completely new cat that it has never seen before, and it will say, probably, it's a cat. So somehow it has learned to generalize what cattiness is, but not in what you or I might think was an intelligent way. But at some level, it becomes hard to talk about what intelligence is, other than how it behaves, and that led Turing to propose the Turing test, which computers have now got pretty good at with chatbots. So this, I think, is all good fuel for really interesting discussions with students about what it means to be human and what intelligence is and what we can trust computers to do and what we can't. Remember, so this issue of trust is very important. We might not mind if it digs up a few bits of corn when it means weeds, but if a computer has learned, say, to predict your chances of being burgled from the information that you've given to it, and therefore decide whether to insure you or not, then you might like it to then it might learn that from tons and tons of data, right? And it spits out a prediction, and then somebody might say, well, why has it predicted that? What could I change about my life, or what might risk? If I add more locks, would that do better? So one way to do it is add more locks and see what it predicts now. But that's not very satisfying, right? You would like to have a more explainable model of AI, so it can explain why it made predictions or why it made choices. That would be that should be quite important. And in places where computers are making decisions, in effect, about things like insurance, or will you get a visa, or will you be allowed granted asylum, who knows? It's incredibly important not to just place trust in algorithms trained by data that might be skewed. I've tried to show you the sort of risks that you get from skewed data. So in this final slide, I'm trying to say that understanding something about how this works puts us in a better position to make good judgments about what AI is good for and what it is not. particularly with AI, if you don't understand it, there's a real danger. I am anxious that we will screw up by just by allowing computers to do things that we really shouldn't let them do yet, or not understanding what they're doing. And yet there are things that they really are very good at, and it is appropriate for them to do, but you need informed judgment for that. And that's why I want every child to learn computer science. Let's just look at some of these other questions. Our perception, Julie asks, our perception can be incredibly, or comments, our perception can be incredibly flawed. That's true too. Our own, we too make the similar mistakes that these, AI systems make. We sometimes make very flawed judgment because we're based on imperfect data. Julie also asks, are we not just taught? Aren't we just big data repositories? Oh, actually, I can't even see the whole of that. Aren't we just big data, taking on data upon data from the moment we're born? Oh, aren't we just big data repositories, taking on data upon data from the moment we're born? Yes, I suppose we are. We're gathering lots of data and learning from it. But I don't want to say that what I've shown you is the way that human beings learn. It might have something to do with the way that human beings learn. Let's see. Are there Chris asks, are there specialist areas of machine learning, face recognition, predictive text? Oh, yes. Right. So there's tons of subspecialism within machine learning. So just take recognizing an image. That is, well, that might be, 100,000 pixels or 1 million pixels. How are we going to feed that into neural network? That's an awful lot of inputs. And moreover, once you'd learn to recognize a big cat, you might like to, would it equally well recognize a smaller cat, just shrunk? Could we find some way of making it or a rotated cat, right? So there's some things you think, maybe I don't want it to have to learn about that. Maybe I could, do some transformations to make it more robust to those kind of changes. And for predictive text, yes, if your images are sort of two-dimensional, text has a sort of one-dimensional nature and some kind of locality. Words relate more closely to ones nearby. So there's an enormous area of research called LSTMs, I think it's long short-term memories or something that machine learning people do that sort of remembers a bit of state about what has happened and uses that to feed into what our learned prediction about what comes next. Predictive engines can do incredibly good at in fact, machine translation is very much based on all of this kind of stuff. Machine translation systems use a lot of machine learning. So short answer to Chris' question, tons of subspecialisms. Just thousands and thousands of people are beavering away with every neuron they have to make this stuff better. Ken asks, where does symbolic learning and reasoning fit in? Good question, because here this has totally abandoned any notion about, if there is a door, then maybe I would want to go through it, or if I drop something, it's likely to fall down. That sort of common sense about the world has been lost in this morass of floating point numbers. So I think I don't know the answer to your question, Ken, just to say that, previous iterations of AI 30 years ago was very much about symbolic reasoning and trying to generate sort of causal chains of reasoning, if then kind of reasoning, and trying to embody and express and articulate common sense and then use that in chains of reasoning. And this is utterly different. So it just as programming is utterly different from machine learning, so machine learning is also utterly different from that symbolic reasoning. But I'm sure there are lots of people beavering away trying to figure out how to make this sort of symbolic reasoning and machine learning sort of work together. Are there tools or products you'd recommend to introduce machine learning to primary school children? Haley asks. I don't know. I don't think I can answer that question, but I could probably ask some other people. I think maybe you should ask that on the CAS community, and maybe some people will cough in. Or if you don't get enough answers, ask me, and I'll go away and try and find out. The one that I found that was most helpful for me was this TensorFlow playground thing, because it was fun and very easy to get to. Lots of other Chris suggests something called Google Quick Draw. Maybe in response to Haley's question. Marla says, asks, where does deep learning fit in neural network? Oh, good question. I should have said that. Back to my slides. When I drew these layers, right, now you can imagine instead of having 2 layers, I could have 3 layers or 4 layers, or in the case of some of these image recognition programs, 150 layers. The layers is the deepness, right? So a neural network is deep if it has many layers. So deep learning just means learning weights for neural networks that have many, many layers. Oh, Angela Defoe suggested machine learning for kids. Maybe you could just, Wendy, before we're done, you could collect some of the suggestions onto things. Oh, machine learning for kids.org. Let's see. Sarah's saying the Royal Society has some lovely infographics suitable for primary. Oh, cool. Search for Royal Society machine learning infographics. Spencer says machine learning for kids is excellent, but doesn't give a URL. There was a Raspberry Pi seminar this summer, a chap in Spain. I'm just reading these out because I think you can't see everybody else's questions. Is that right, Wendy, that people can't see each other's questions?
Yeah, that's right, yeah.
Yeah, so maybe we could sort of collect the questions. There's a lot of interesting suggestions, and other people have mentioned apps for good and Scratch for machine learning. Oh, Julie's, there's a sort of machine learning interface for Scratch, yes. Teach table, there are lots of suggestions here. Good. This is very helpful. So Wendy will collect those and make them available in some form afterwards. Good. I think it's 10:58, and I know that something else is starting at 11, so we should wrap up there. It's been a great pleasure to share this with you. I hope you've enjoyed it. I really want to give you a sort of visceral sense of the excitement of that how we can take something so simple as the stuff that I've shown you, and by applying really whole data centers of computation to it, do something that is completely astonishing. And that for me is part of the essence of the excitement of computer science. You can do something amazing with some simple ideas. Thank you.
Thank you so much for joining us today, everyone who's tuned in, and a special thanks to Simon for presenting. Please share your highlights from today's session via social media and the CAS website. At the end of this webinar, a short survey will appear on your screen, and we'd be really grateful if you could take a minute to complete the survey. Additionally, in about a week's time, you'll receive an email with a CPD certificate confirming your attendance at the session. A recording of this webinar will be available on the CAS website in the near future. And coming up next, we have sessions on Everyone Can Code and Swift Playground, and Is It Logical? Considering the notion of powerful knowledge in the teaching of programming. We hope to see you at other sessions, and please do continue to spread the word about the first ever CAS Virtual Showcase. Thank you so much for joining, and I hope to see you next time.
Bye.